Alright, so just talking through. So there's any so recursion. Just a quick recap of what we have covered so far. With recursion, we're going to talk. We have talked about just the concept of termination conditions and decomposition. We first looked at how you can solve some numerical problems using that construct. Next, we looked at how you can actually solve some data structure related problems. So for example, we did one with a linked list. And then lastly, how you can actually take some interesting and at the face of it, rather challenging problems and turn them into a very simple piece of code, where the example we used was the maze, where the idea is that you can actually take a maze and create a newer version of the maze, which is a shorter, simpler version of the maze, and keep recursing down that path until you find a solution to the maze. So that's kind of the broad spectrum. And then my TAs tell me that on Friday you guys did some additional exercises with solving challenges with recursion and some more intermediate level problems. So before we move further, I just want to be sure that I answer any questions. So any questions or anything that's unclear about recursion at this point? Yep.
In our lab for this week, we're supposed to find the square root with two different types of recursive decomposition styles. So one's n-1 and the other's n divided by 2.
That's right.
So I was wondering, like, about the n divided by 2, what would be the advantages of doing that? Because I had to call the function twice.
Sure. So that's a great question. So the question is, and I would not answer it for the square root, but I can answer the question in a more general context. So in general, we would actually refer to these as a numerical search problem. What you're really trying to do is, I have an answer. I just know that the answer lies somewhere between 1 and 100. Why 100? Because we are looking for a square root of 100, let's say. If I'm looking for a square root of 100, we know enough math to know that the answer, while we don't know what it is going to be, is somewhere between 0 and 100 itself, and in fact, not even inclusive. So it's really 1 to 99. We just know of a large space in which the answer lies. It's somewhere on the number line, if you will. So if I was to draw this number line, it starts right here, 99, and somewhere in here is an answer. We know the property of the answer. We know a property of the answer, which is that the answer, which is x, when multiplied by x, will give us the final number, which is 100, which is what we're looking for. And what we're trying to find is, what exactly is x, right? So what you're really trying to do is a search. Now let's just say, what are some of the ways we can do a search here? So you can actually start a search by saying, I start at a 1, and then I'm going to try 2, and then I'm going to try 3, and then I'm going to try 4, and then I'm going to try 5, and then I'm going to try 6, and just keep going. At some point, we're going to get the answer. Thumbs up, you break recursion, you're done, right? That's one way of doing it. The alternate is that rather than just doing a +1, I take the space and I say I have 1 and I have 99. I know my answer is somewhere in the middle. I just break the space into 2, right in the middle. I say, let's say the line gets drawn straight at 50. Is the answer to the left or is the answer to the right? That's the only question you need to ask. By knowing that 50 times 50 is in fact greater than 100, we know that since we are looking in the middle, the answer is not going to be to the right, because 50 times 50 is too big, right? That's just us using our mathematical sense. That means my answer is going to be somewhere in here. I have a mechanism for searching between 101 and 99 for my x. That's what we had before. Now I have just shortened that space and said it's, rather than it being between 1 and 99, it's between 1 and 50, half of it. So I can take that same function and call it yet again on this space. Same algorithm is going to operate again. We'll just split it up into two. This time the line gets drawn at 25. To the left or to the right? To the left. Same algorithm, same function, just call that again, but this time on the range between 1 and 25. Next, break it yet again. Line gets drawn at roughly 12.5, so we'll just call it 12. Now I'm looking for my answer between 1 and 12. Better. Yet another line. The line gets drawn at 6. I have 1, 6, and 12. This is where we are looking. Is the answer to the left of the line or to the right of the line this time? To the right, because 6 times 6 is less than 100. So that means I'll take this range and then recurse down here again. So you just keep recursing until you get to the answer. And it's actually a very, very common method. It's square root is just one example of this. But there are many situations where it's actually easier to find the answer by just searching through the space rather than actually trying to solve the equation, if you will, which is, in this case, we're really trying to solve the equation. We're saying, for what value of x will x times x be equal to 100? And mathematically, it's sometimes easier to just do a numerical search for a wide range of x and just keep recursing and keep doing that search until you actually hit the final answer. So there's a couple of things here to worth noting. One, for us to do a numerical search, your search should not be between 1 and infinity. That's too big of a search range. You have to have some mathematical property that tells you that it's going to be between here and here. It has to be a finite range before you can apply this method. For a square root, we know enough maths to know that the square root of a number is going to be less than the number. Unless the number is 1, the square root is always going to be less than the number. So that's how I came up with the 1 and 99. The second thing is that by drawing a line in the middle, you ought to be able to tell whether the answer is to the left or the answer is to the right. As long as you have a mathematical problem that you can break it down into two things, I have a finite range, and by dividing that range, given a number, I can tell if this number is greater than the answer or less than the answer. Just the combination of those two means that I can take any mathematical problem and just solve it using recursion. I just need to know what is the maximum range, and given a number, can you tell me, if I give you the number, can you tell me whether this is to the left or whether this is to the right? And that'll give you the answer. Make sense? Let's actually, while we are talking on the subject of search, going through a telephone directory, we actually use this algorithm a lot ourselves as well, right? When you have a telephone directory and you're trying to find a number, assuming that everything is in alphabetical order, what do? Or if you're looking for a particular thing, very typical, you just open it right in the middle. You know that it's a finite search because it's going to lie between page 1 and page 500. That's what the directory is. You open it right in the middle, which is the same thing as drawing a line in the middle. You know that the last name starts with a C. If I open it in the middle and I see last name starting with N, I know that I only need to go towards the left. I don't need to go towards the right. And then I take the next half and again break it up. And then keep doing that until you actually get to the page where C is. And that's exactly what we are doing. We know two properties, the finite range and the ability to tell greater than or less than the answer. Yes?
So the base case would just be whenever you split and you find an x that happens to equal 100. Is that the base case?
That will be a termination. When you have actually found an x, when the answer x times x is equal to 100. That would be your termination condition. And so if x times x is equal to 100, thumbs up. Else, divide the range and call the same function again to check.
But doing that, would it be possible to skip over the x?
So there's mathematical intricacies in that you can actually get skipped with the 0.5s and stuff we are playing. So you do have to be a little careful, and that's what makes the problem a little more interesting. Otherwise, this will translate, what we just described here will actually translate into about 4 lines of code, literally. So there are some intricacies that you have to think about and be careful with. So answer your question? Yes. Any other questions? Again, anything about recursion that we've covered last week? All right, so in that case, we'll just keep going. And by the way, just re-emphasizing the same thing again, I was when my TAs told me the lecture didn't go very well, I was really hoping, I literally was checking the feedback form every day, hoping that somebody else would say the same thing. So please take advantage of that. Do let me know if a lecture is unclear. Thanks for the fact that the TAs are sitting here to tell me that, but if anything was all over the place or not clear, please let me know through the feedback form. That's the reason it exists. That said, let's keep going into the next topic. This is a rather bigger shift from what we have done so far, but it's a change for the better, as you will see, because a lot of the things that you have done so far manually, as I would call them, would actually be taken care of by the compiler for you when we are moving over to C++. And there are some very useful constructs that will get added to our toolbox that we can take advantage of when we are working with C++. So a couple of announcements, by the way, also before we start today's lecture from my TAs. One, we did follow through on our promise. I believe the video was actually posted and everything was all done at the right time this time. Second, as promised, the lab assignment was posted today instead of Wednesday, so it's already available if you want to take a look at the next lab. And third, the TAs are going to post a small subset of recommended problems that you want to practice on your own this week. So what we have thought of doing is that this week you'll be given sample problems from the subject that was covered last week, so on recursion. So the flow is we go through some stuff on Monday, we do some laptop work on Monday, more laptop work on Wednesday just to see some real examples. Post the videos. Friday you show up to the TA session and they have you go through the exercises. And the following week you get some more assignments that you can do on your own just to gauge yourself. And the TAs will also post this. So they'll post the problems tonight and post the solutions next Monday and then the next set of problems from the stuff we'll cover this week. Does the flow make sense? Any comments? Okay. So you will see an email from one of my TAs later today. So moving over to C++, let's first start by talking about why C++. And the motivation is pretty clear. It's the next generation programming language built on top of C. It's 100% backward compatible, so anything you can do in C, you can do in C++, which means that you can really take your C program that you've written so far, push them into a C++ compiler, and they will still compile and work. But what C++ does is it actually tries to take away some of the shortcomings of C. The reasons those shortcomings exist, in my opinion, I mean, it's just an opinionated statement, but there were two things that happened. One, after people saw how C was being used, there was a lot of learnings that were made. And then overall, the field of programming actually advanced a little from when we got from C to C++. So a couple of very major shifts happened. The biggest one was the idea of object-oriented programming got really prevalent between the time when C was started and when C++ came around. So the major difference that you will see between C and C++ is that C++ has a lot more constructs for object-oriented programming. And when I said there are a lot of things that you guys were doing manually, some of those, and you'll see that what I mean by that here in a moment, would now be taken care of for you by the compiler. It's just a smarter compiler. It's a much smarter C compiler. Can do everything that a C compiler can do, and can do a few extra things that we will be talking about. Again, object-oriented design is at the core of it. So a lot of the things that we will talk about have to do with object-oriented design. So let's actually start with the example, the program that you guys just worked on, the set-adt. So remember that set-adt had a very specific way the code was actually written. So your set, there was a header file. In the header file, there was a struct. The struct actually contains the actual elements array, the pointer to the elements, the length, the capacity, and a few other data portions. Right underneath that struct, there were a few functions that were defined. Each one of the functions actually has a specific way it was actually interacting with a set So there was a function for isMember that would actually check if something is, the input is a member of the set. There were other functions around union. The key is that each one of those member functions, if you recall, also had a pointer called the self pointer. Every one of those pretty much took, and as its first argument, took a pointer called the self pointer, right? So there was kind of a very specific pattern there. There is the struct with the data. There's functions. There's functions which have self as the first pointer. That specific way of writing code actually comes straight from the book of object-oriented programming, where the idea is that, remember we did that Facebook structs and stuff? Every one of them, we actually had some data and some methods that you can operate on them. So there were user was one of the structs. There were certain things that you could do with the user. We actually wrote them down as print a user, print timeline for a user. There were some functions that we wrote underneath each one of those structs. That's kind of the way object-oriented programming works, is you think of things as objects. Each object consists of a set of data and a set of functions. Typically, you would refer to the set of data as data members and the functions as member functions. So you have data and functions. In C, we were enforcing that object-oriented methodology by saying there's a header file with some struct and some functions right underneath. All of these functions work with the struct that's defined right above it. And could you write any arbitrary function inside that header file? Could you define an arbitrary function which had nothing to do with set? Could I put a function called print my name in that header file? Sure, there's no restriction to that. You wouldn't do that just because it would be non-customary. With C++, they actually put a real construct for defining member functions. So when you actually define an object, just like you define data members and structs, inside of structs, in addition to the data members, you can actually define the functions related to that object right inside the struct itself. So what that means is that I actually have a struct, let's say set. Everything's pretty much the same. I have elements. I have capacity. The length. But now the isMember function, rather than putting it after this with a self pointer, you can actually put a function, put the data function, the actual member function right inside the struct when you're dealing with C++. So we can literally say it's a Boolean isMember. Let's say we have a set of integers and you're actually checking. And in fact, you can actually declare the function right in here as well. So you could actually put the contents of the function right in here, or declare it right in here. So there's two things that are very interesting about this. One, in fact, for now, the one that we're actually able to put functions right inside of structs, something that you are not able to do in C. In C++, you can define it right inside the struct. The other thing that happens is, notice that I did not put a self pointer here. Remember that there was a self pointer when we had any of the functions that we were dealing with set. There always used to be a function, a pointer called set star self, right? I did not actually put in the self pointer here. This idea, the whole thing originated from the fact that a lot of people were doing that in C, which is they were creating member functions, they were putting them right after the structs, they were always putting a thing called a self pointer. What does C++ do? Two things. One, you can now put your member functions right inside the struct. Two, the self pointer becomes what we call an implicit argument. So you don't write the self pointer, but it actually gets passed into your function by the compiler. Since programmers were doing it over and over again, they figured there was no point of asking the programmers to do it, and the compiler will just take care of it. So even though we write it as isMember int x, in reality, this function is taking two arguments. One is the equivalent of the self pointer, and 2, the int. The int is an explicit argument. The self pointer, which is not shown here, is because it's an implicit argument. The compiler passes it in for you. And there's actually a name. We don't call it the self pointer in C++. The self pointer is called a this pointer. Just a naming thing. Really, it's the exact same reason why it's passed. Just that it's called a this pointer. So the variable is actually called this. Inside of this function is member. There is a variable available to us called this, even though it's not declared, because the compiler actually injects it in for us. If you actually open up the stack to see what the activation frame for this function looks like, you're actually going to see 2 arguments and not 1. One explicit, one implicit. But that's what C++ just takes care of for you automatically. Anything that's a member function is automatically going to have a this pointer passed in. Anything that's outside of the struct will not have a this pointer. So remember that if you want something to really have that self pointer passed in, then it's best to just put it inside the struct. Because then you'll get the this pointer passed in automatically.
Professor,
Yeah.
what does the this pointer do?
So this pointer is a pointer to the struct that you want to be. So remember how you were dealing with the sets, and you're passing in a pointer to the set in which you wanted to find the member. Here, this pointer is saying when I declare a set, let's see how would you actually use it. That might be one of the easiest ways to doing it. If I declare a set called, say, set A, I can then just call a.isMember. And give it an argument. Notice the dot syntax. This is the exact same syntax as using data members that we were doing in C. Now you can do the same with member functions. I can do a dot, the name of the function, and pass in, notice again, just the explicit argument. I did not have to care about the implicit argument. What's the compiler really going to do inside of this? It's really going to call the function isMember. Remember that this is the commented out part, because this is what the compiler is really going to do under the hood. For this pointer, the first argument, it's actually going to pass in the address of A. How does it know that it needs to pass the address of A and not something else? Because we did an A dot isMember. If it said B dot isMember, the compiler would have passed in the address of B. And then the same argument, and this is what the real function call looks like under the hood. At the face of it, we just use this very convenient syntax. Set A is to be a member of A. Just write that. Under the hood, the compiler is going to say it's a call to the isMember function. The self pointer is going to be equal to AND of A, the address of A, and the argument is going to be the same. That's equal to 3. So the compiler takes care of this translation for us. Easier, cleaner code to read and mess with. The ugly piece gets taken care of by the compiler itself. Now, within the isMember function, again, when I am writing or declaring that function, there's actually a couple of ways of doing that. So, go with simpler mechanisms first. Now, inside the isMember function, this is a member function. If it's a member function, even though it does not say that, there is going to be a variable called this available to us that we can use. So my code is going to look something like this. This to the length. Since I'm going to check for isMember, I'm most likely going to add, what I'm most likely going to have is a for loop going through all the elements of the set. So my code is going to look something like for int I is equal to 0, I is less than. Now we are talking about length. So if you go back and look at your isMember function implementation from the previous lab, you will notice that you were doing self to the length. That's exactly what you were doing, most likely in your code. Then we have I plus equal 1. And then the rest of the code will just follow, which will be something like if this to the elements equal to x, you could just do a return true. Else return false. But the key is to note that the self pointer just got replaced by the this pointer, and the second key aspect is that this pointer is not declared by you, it's taken care of by the compiler. How does the compiler know what to pass in as this? It gets that from us doing that. Now there's actually another possibility here, which is I may have declared a pointer to a set, and then maybe created a set dynamically by saying set b is equal to malloc size of set. Rather similar to the code that you guys have written in some of your functions too. Now what happens if I want to call isMember on b? This is a pointer. What syntax would I use? How will this be different? It'll just be the arrow syntax. So nothing too different from what we have done already. You can do b to the isMember 3. Under the hood, what the compiler is going to do is it's going to call the function isMember. The first argument, what's the first argument going to be for the isMember function here? What would it need to pass in as this address of what variable?
So b.
B. It would be the address of what we declared here, and since b is a pointer itself, we can just pass b, the actual pointer itself, and then 3 as a second argument. Again, we are writing a simple one argument thing. The compiler is taking care of everything else for us. Inside the function, we are assuming that there is something called this that will be available to us. So eliminates the need for writing. If you go back and now look at your set.h in set.add, you'll see what I'm getting at, which is your functions are extremely repetitive. isMember, set star self, next function, self star set, next function, self star set, set star self, one after the other, 10 lines. Eliminated all of that, gets taken care of by the compiler for you. So this is one of the biggest things, the ability to put member functions straight inside the struct. And second, the fact that you actually get at this point for you automatically. Yes.
Can you change the value of this?
Can you change the value of this? You can. It's a pointer that gets passed in. So I can always do something like, if I'm inside a function, I can do something like this to the length is equal to 5. I can change the length, which is not the same thing as changing this, but I'm changing what's pointed to by this. The question is, can I do star this is equal to something else, which is really, what is this pointing to? Dereference this. I could do that too, so I can actually say star this is equal to some other set, and one set gets copied over. Can I change the value of this variable? Can I just say this is equal to 3, for example? This line of code will compile. This will need to be a valid pointer, and you'll have to typecast it, obviously. But the code will actually compile. But will this actually change this pointer? It won't. Remember, because this is actually passed in. What gets passed in is the copy of the variable, the pointer. So you're not. What we're passing in is this pointer. This pointer is, to be explicit, is of type set star in this case. If I change the value of this, I'm just changing the value of a local variable, something that has been passed into me as a part of my activation frame. You can change it, it's not going to do anything useful. So you probably don't want to change it. But there are some funky things that you can do, like you can actually do star this and actually make it point. Change the context of, for example, A, B in this case, and A in that case by doing a star this is equal to something. Or I can individually access the elements and change their values as well. So I have everything that I can do with the self pointer. It's exactly the same thing as the self pointer. Just like with the self pointer, you guys were able to change the contents of the set that it was pointing to. That's good. You can change, for example, the size of the elements array. You can change the length, whatever you wanted to do. If you actually change the self pointer and set, and if you go back and look at your code, I doubt you'll find a single line of code where it says self is equal to something. And the reason is because self pointer it's a local variable. Changing it is not really going to help. It's just a passed-in argument. It's not going to have any impact on the rest of the code if you change it. So you don't want to change it. You can change it. The code will compile. It's not going to do anything useful. Yeah.
Start this is just gonna basically change the value of the first element. Right?
No, it's actually going to change. So the other side will have to be some kind of a set, and it will copy the entire set over.
Isn't this isn't start this the address of element, like the first element?
So we have a struct here with this data. And by the way, just going on small digression, worth mentioning that what gets when you declare set A, what gets saved in memory is only the data element. It's not that the member function gets copied every time you declare A or every time you declare a new set. The member functions are really, and can't emphasize this enough, the entire idea is based on convenience. It's not really changing how anything is done from the way set ADT was done. Literally, everything is under the hood the same. The only thing is that it's very convenient to work with. So when you write your functions in here, it does not mean that if I did a set A, comma B, comma C, now I do not have 3 copies of the isMember function. No, you still have only one isMember function. There is 3 copies of the data elements, 1, 2, and 3 for A, B, and C. What you do not have is multiple copies of the isMember function. So functions that you write in here are exactly the same as declaring them in a header file. There is no difference. The only thing is that now the compiler takes care of them passing into this pointer for you. Now, coming back to your comment earlier, which is the idea that if, so we have the member function, this pointer gets passed in. When you do a start this pointer, remember, is of type set start. So when you start this, now you have a set over here. If on the other side we actually pass in a new set, let's call it, and I'll call it set Z, and I just say start this is equal to Z. Now I have just overwritten the actual set. You can copy a struct over the other. So it's just going to copy byte by byte all the bytes in Z over to start this. And start this is actually of type set, which means it includes those 3 integers. So 12 bytes will actually get copied over, 4 for each of the 3 integers. Well, one's a pointer, so again 2 integers. So 4 plus 4 plus 4, 12. Does it make sense?
But I feel like start this is gonna be the address that elements pointer is gonna point to.
So start this is a point. So it depends on the type of this, right? When you do a start reference on a pointer, it's a type. It's a set type, right? So when you do a start this, it's now a pointer to a set. It is actually the case that it's accurate that the actual numerical value of the address is the same as the first element, but it does not mean it's going to be an integer pointer. What you won't have is start this is now an integer pointer, or now a pointer to an integer pointer, which is it is in this case. It's a pointer to a set. When you deal with it, it's a pointer to a set. Like your self pointer was basically. Like the self pointer that you were passing around in the set ADT is a pointer to a set.
And to the first element.
And it's to the first element, but that does not mean that when you do a star on that, it actually gives you the entire set when you do a star on a pointer. Right? If I wanted just the first element, I would have to do something like this. I would have to say that this is really an int star dereference. This is what I'm going to have to do. I'm going to tell the compiler. Otherwise, to the compiler, this is a pointer to a set. And when I dereference it, it will give me a set. It won't give me an integer. It will give me a set. It's a pointer to a set. I dereference a pointer to a set. What do I get? I get a set. I don't get an integer. Make sense? Other questions? Alright, so again, member functions, this is the implicit argument, and there's a few special kinds of member functions that we'll just jump into next, but let me take this question first.
Is this a pointer to a pointer?
No, this is not a pointer to a pointer. This is really just a pointer to an object. So this is of type set star, which is you have set, which is an object, and you have a star, set star. That's really the type of this. Now, whatever the struct type is, that's basically what this points to. So if it's a struct set, then it's a set pointer. If it's a struct maze, it's a maze pointer, and so on and so forth. It's really just, but it's not. It's a pointer to the object. It's not a pointer to a pointer to the object. Makes sense? Yeah.
So in terms of the activation frame, since you said this is a implicitly given, does that mean it's always going to be argument number one? Like
It's always argument number one. That's a great point. And it's always argument number one. It's not a coincidence that I put this pointer value first in both cases. It's always argument number one. So if you actually look at the activation frame, you will actually find it to be the first argument. Any other questions? So we'll just keep going. So struct, we have some member functions. There's two ways to declare member functions. This is a little of a syntactical thing to understand. When you define a member function, so one option is to define a member function by defining it right inside the struct, like I did over here. It's basically inline definition. So I said bool is member in X, I put curly braces, I put the function right there. All of this is still inside the struct definition, right? There is actually another way of doing it, which is, and let's do it with an example. So let's say that there's another function here, and what I'm going to do is, let's say that there's another function here called union. Notice that in this case, I did not put the curly braces, I did not do the definition inline. Instead, I put a semicolon, like I'm just declaring a function that it's going to exist. It's set star, union, set, and other. Notice that again, I did not pass in a self pointer. Its only pointer is the other pointer, which is the other set that I'm going to take union with. How does one declare this function? I have not declared it inline, so this is just a syntax to remember. Another way you can declare functions in C++ is that later, when you're ready to declare that function, you'll just do set star, which is the return type. And this is kind of the key thing. Set double colon union. And then I can just do the rest of the function declaration, set star other. And now I can write my code for union right here. Now, how does this work? Well, putting that, so notice that this is not any different from just the union function that we have dealt with in the past. But the key is by putting in set colon colon, what I'm doing is I'm telling the compiler that this union function belongs to the struct set. It's defining what we call the scope of where the function is. So this union function applies to the struct set. And the compiler is going to do its matching. It's going to check that struct set does indeed have a union function, which was declared but not defined. And that over there, somewhere else in the code, is a definition of this function. And it'll just link the two. We use them both, so sometimes you'll see code written inline with C++ functions, member functions. Other times you'll just see function name with a semicolon at the end, and the function itself defined separately. Not really. Usually the best practice you'll notice is most libraries, code that is to be reused over and over again, prefer to do it inline. The advantage of doing it inline is that now you get the function definitions and the declarations all in a single header file. Anyone who includes that header file gets it all, basically. They don't have to do anything else. You just type on include this new struct and gets everything, all the definitions, the functions, the members, whatever. Other cases, what people will do is just put the struct definition in the header file with not defining the entire function, but just declaring them, and then defining them in a subsequent C file. So for example, a set.h, which has the struct set, and the member functions just declared, and then maybe a set.cpp where these functions are defined very similar to this by putting a set : in front of every function name. Technically, they're exactly equivalent. Underneath the hood, the compiler is going to take that and turn it into this. But that was a convenient way of doing it. The inline mechanism is just a convenient way of doing it. And we'll switch back and forth. I generally, in my programming, most of the times use the inline. I actually find that ability to see the function and its definition right there very handy. But there's a lot of programmers who actually prefer to do it the other way as well.
So basically, if you write that inside the struct, then you have to write that in a different file.
In a different file, yes. So if you write that inside the struct, the compiler is going to buffer you saying the function has not been defined until you write that somewhere else in your code. It's very similar to what we had in the set.h file where the functions were just declared but not fully defined, and then you guys went in and defined some of the functions that we had not defined fully for you in the CPP file. It's very similar to that. So in your next programming lab that you'll be doing, you'll be doing the CRM once again. Remember the CRM lab we did? But this time you will actually do it in C++ instead of C to see the contrast. And the major difference you will notice is that instead of those .h files, the structs will not just contain the struct and then followed by functions, but contain structs with member functions and the use of this pointer. So similar algorithms, but will be rewritten, code will be rewritten from C to C++. To just kind of show the contrast. So a few things again to carry forward. One, member functions. Two ways to declare them. Either you just declare them and define them somewhere else, or declare them and define them right there inline. Technically exactly the same. If you open up the contents of the memory, they will actually compile to the exact same thing. The only difference is that in this case, you are doing it conveniently and the compiler will convert it into that for you. Under the hood, in fact, the reality is, and worth noting, under the hood, the function name, the compiler is actually going to give it a new name called set : union. Even if you do it that way, it's just going to take care of it for you. And you can actually define it explicitly later on. In fact, while calling the function, you can also call it like this and it will actually compile. If you use set : it actually does compile. It's a bit freaky because nobody actually does it that way. But the reality is that the compiler does recognize this as a valid name for the function union. So you can either just say b.union, or you could say a.union, or you could just say a.set : union, and the compiler will compile both. It's really the same function under the hood. The compiler is just making life convenient for you. The other advantage of this is that now we can have two functions called union. I may have a struct called set, in which I have a function called union. I may have another set where I may have another struct for a different data structure where I also have a function called union. They can both coexist because one is set : union, the other one is my other thing : union. So this is why the compiler does it. It allows you to have two functions with the same name, and the compiler automatically attaches the name of the struct to the function name so that you can have two functions with the same name coexist. And the compiler will know which one's which automatically. Make sense? So there's another very important aspect of C++ that there are some functions that have special meaning to make life even easier. Was there a question? So there are other some functions that actually have specific meaning in the context of the language. Again, the compiler is trying to be helpful to us. So among other things that the compiler can do for you, just like this pointer, there is three special kinds of functions that we call the constructor, the destructor, or a deconstructor. I've seen it being called both. And there's another concept called a copy constructor. Remember in your set ADT, there were two functions. One was create empty set, and the other one was create a set with one element. Remember there were two functions there? What they would do is they would basically give you a set back when you call that function. Those functions were literally an example of constructors. They were both constructors. A constructor is a function that creates or initializes a set for you. A destructor is the one which destroys it for you, and we had equivalents of that in the set example as well. A function that would actually deallocate the elements array and delete everything that's related to that set. And then we'll get to the copy constructor, but a copy constructor is called, it's a function where you say, I want a copy of this set. If I want a copy of this set, I call the copy constructor. So I have, again, a constructor, a destructor, and a copy constructor. All three of them are member functions, and they are member functions with a special meaning. So for each one of them, we'll try to answer two questions. When is that function called? And two, what is that function, what is the purpose of that function for each one of them? So let's start with the constructor first. I'll leave the set example up there. So before we start removing the pieces. So typically the idea behind the constructor is to initialize the data members. That's what a constructor is called for. Its job is to initialize the data members. So when I call a constructor for set, and this is kind of the tip, when you are writing a constructor, what you want to do is literally use your data members as your checklist. A valid constructor or a well-written constructor should initialize every single one of the member functions to a valid value. That's its job. So for set, if I'm writing a constructor, the constructor, by the way, can take arguments. So it's just a regular function, really. And guess if you don't pass in any arguments to the constructor, what is the one argument that still gets passed to it? Is it this pointer? But it's just another member function. So this pointer is always passed in. So first of all, how do you declare a constructor? Let's start there. So I will have to make myself a little more room here. So first of all, you have to declare the constructor. How do you declare a constructor? I said it's a special function. It's a special member function. The way the compiler recognizes a constructor is that the name of the constructor is exactly the same as the name of the actual struct. That's how the compiler knows that the programmer is talking about the constructor. This is the only thing you have to tell the compiler. It's smart enough to know that if the name matches, it's going to assume it's the constructor. The converse is never use the name of the struct as the name of the function if you don't want this to be treated as a constructor. So the constructor is, in this case, let's say set. I'm going to first have the constructor, and the constructor never returns a value. It's, again, like I said, it's a special function. Same name as the struct. If I pass in no arguments to the constructor, then effectively it has only one argument, which is this pointer, like everything else. You can actually have more than one flavors of constructor. Remember that you had two flavors of constructors in your set ADT. Create empty set and create a set with one element. There were two different flavors of constructors. In both cases, what those functions did was they initialized the data members. So we're going to just copy the same thing over here. I'm going to assume that my set with no arguments, my constructor with no arguments, is that constructor of an empty set. Sounds fair? So let's write this out. I'm not going to do it inline because we're running out of space here. So what I'm going to do is just do the double colon syntax. So set colon colon set no arguments, and I can write my constructor in here. This is going to construct my empty set, which implies that I'm going to do this to the elements is equal to null. Exact same code as what you guys wrote, except this is written with this, and this to the length is equal to 0. Is this a valid constructor? Remember, to check if it's a valid constructor or not, make sure that every element, every data member is actually being initialized. Is it being initialized right now? Yes, it is, so we are good to go. Let's write another constructor. I'm just going to say this is a constructor that takes one argument. This constructor will create a set of size 1 with k as its the one element that actually gets passed in. So say we do set int k. What I do in here is exactly the same as what you guys were doing when you were creating a set with just one element. So this to the length is equal to 1. And this to the elements is equal to same thing, which is int star malloc size of int and then lastly this to the elements 0, which is the first element, is equal to k. Now I have two constructors here. One is set and the other one is set int of k. Both of them are constructors. Remember the job of the constructor: initialize all data members. More than one constructor are possible. They have the exact same name, and this is where C++ gets a little interesting. C++, notice that there are two functions with the same name. If you try doing this in C, the compiler is going to bark back at you real bad if you try to have two functions with the exact same name. In C++, there is a smartness that got added, which is what we call function signature matching. You can actually have two functions with the same name as long as their signatures are different. If their arguments are different, the compiler will actually allow them to coexist. So now you have two functions named set. One takes no argument, or one implicit argument, and the other one takes only one argument, one explicit argument. Now both of them have been defined there, and I'm telling you that the compiler is not going to bark back at you. How will the compiler actually know which one of these two to call when you call a function, when you make a call to this function? Based on the arguments. It's going to accept, when you call it with no arguments, it's going to assume you want this guy. If you call it with one integer argument, it's going to assume you want this guy. If you call it with some random string argument, what's it's going to do? It's going to bark back and say, actually the error is going to read something like this: no constructor found that takes string as the argument. If we wanted a set to be declared from a string, we'll have to define yet another constructor. Yeah?
What happens if we say that we write the constructor and then we set the return value as void, return type?
What happens when we write the constructor? We just type the return value as void. It's actually not accurate. The return value is not really void on a constructor. It's just implicit. It's under the hood that's taken care of. What it really is it's a pointer of type set. That's what the return value is. But you don't need to even write that out because the compiler will take care of it for you.
Well, if you do void, then it's not gonna.
I have not tried it. It might, most likely, it'll give you an error. Just like the constructor, so first things, like I said, for every one of those three special functions, constructor, destructor, first, what is the constructor for? It's for initializing the elements. When is the constructor called? So a constructor is called when a new variable of type set is declared in your code anywhere. So if you do set So if you just did set A, that means we just declared a local variable A of type set. The compiler is going to create A, and then it's actually going to call the constructor. That's one place where it's called. So local variable declaration is one case when the constructor is called. Another one, global variable declaration. And there's actually a third one, which is when you create a new set in dynamic memory on your heap. I won't actually get into this because C++ dynamic memory works slightly differently than C, so we'll spend more time on this next time. But the key things to remember are local variables declared, global variables declared, or anytime a new set is created anywhere in your code, when you say set A, a local variable is created, your constructor is going to get called. Now, which of the constructors will actually get called over here when I say set A? First of all, is that a problem? Like, the compiler does have to solve that problem, right? Because there's two constructors defined. So the compiler is going to have to pick one. Which one is it actually going to pick here?
First one.
It's going to pick the one that takes no arguments. That's the default. And in fact, there comes another small definition. That's why a constructor with no arguments is called a default constructor. When you don't know what to do, just use that one. That's kind of the typical. So set of A, when you do this, automatically a new struct gets created and the constructor gets called, which sets your elements to 0 and your lengths to 0 as well. This is the kind of thing you'll have to do yourself in C. In C++, it's all taken care of for you. You just type this line of code, it takes care of identifying the correct constructor and actually calling it for you, hence initializing all your variables automatically. Remember that discussion we've always had about, I have just declared a local variable, I have no freaking idea what its value is. That problem begins to go away. Because now you know what the values of your variables are, since a constructor gets called that initializes those values correctly. And you don't have to do anything special for it. Just define a constructor and it'll take care of it for you. If you do not define a default constructor, then we are back to where we were, which is it'll just create a struct. No constructors will be called. If you define one, the compiler will call it for you. Very convenient feature to have. Local variable, global variable, and when something new is created in heap. Similar to a constructor, we have this other thing called a destructor. And destructors, again, will just answer the exact same question. Why is it needed? So the job of a destructor is to uninitialize or destroy anything that was created by the constructor. It's typically considered as the exact opposite of the constructor. Anything you create in a constructor, you have to destroy in your destructor. So, yeah.
Before getting this constructor, on the constructor, how do you call the other constructor, the set in K?
How do you call the other constructor? So my plan is to get on the laptop here in a moment. We'll actually look at a couple of examples very quick. So let's just wait till that. It's a syntactical thing. It's not really, there's nothing smart about it. So the destructor, first thing, you actually declare the destructor. There's actually a very special naming for it as well. It always takes the same name as the struct as well, except the name actually has a tilde in front of it. So you literally put the tilde character and put the set right after. And the compiler is going to assume that you mean the destructor here. That's what it's going to assume. So you mean the destructor, we are allowed to declare a destructor. The destructor is supposed to undo everything that the constructor does. Typically what that means is if the constructor actually sets particular values, like elements is equal to null, length is equal to 0, just leave them alone, not a big deal. What you do want to undo for sure is if your constructor actually did something with dynamic memory. That's very critical. In this case, the constructor has, in fact, declared dynamic memory. You want to be sure that your destructor frees that dynamic memory up before it leaves the loop. Because the destructor is called when the object is going away, it's about to die. So I created a local variable, it's about to go away now. That's when the destructor is going to get called. And hence, when it's actually called, what you want is everything, especially dynamic memory that we declared, should be removed. So I would almost say the job of the destructor is to free up any memory that was allocated by the constructor. It's really just that simple. And you can almost use it as a checklist. The way I write my destructors is I just look through the constructor. If there's more than one of them, then look through all of them and just check, make sure that I undo, anytime I see dynamic memory, you want to undo that. In this case, you'll have to be a little smart. Your destructor should check if the length is 0, it should not do anything because there is no dynamic memory allocated, right? If the length is greater than 0, it should just free the elements array. So if, literally 2 lines of code, if length is equal to 0, return, nothing to be destructed, else, free elements, and then return, you're done. That's basically what the destructor does. When is the destructor called? It's very analog to your constructor. So a destructor is typically called when, if it's a local variable, it's called when the variable goes out of scope. This is really a one-to-one mapping here. When will the global variable, when will the destructor for a global variable be called? Anyone want to venture a guess?
Program's over.
When the program ends, when your main returns, program's over. And anyone want to venture a guess for number 3? When will the destructor for a variable in dynamic memory be called?
Whenever you pick it.
Whenever you, what, say it again?
Whenever the user picks it to use those.
So the destructor is called whenever you actually call the equivalent of free. Whenever you're actually about to remove the variable from dynamic memory, that's when you call the destructor. So you call the constructor when it's added onto the heap. You call the destructor when it's removed from the heap. So the destructors, when they are called, we've kind of looked at both examples, the way you actually declare them, and sort of a side note, keep that C++ freakishness in mind, where C++ does actually allow 2 functions with the same name to coexist, which is kind of interesting, very different from C in its flavor. And this property of C++ that you can have 2 functions with the same name but different signatures comes in really handy because you can really declare multiple functions, different signatures, and the compiler can on the fly choose the right version for you automatically. So while the projector and everything is coming up, let's actually try to answer one question that came up from a student earlier, which is how do you actually get the second constructor to be called when declaring a local variable? That was the question, right? If I have a set A, and everyone said when we call set A, it's going to call the default constructor because it does not take any arguments. What if I wanted it to call the second constructor? I want it to be a set of size 1. The syntax for that is I can actually do a set, say the name B, and I can actually declare a variable like that, set B, 1 argument. The 1 argument is an integer. Now, which of the constructors is going to get called? It's going to be the second one, because the compiler is going to realize that the programmer is wanting the second constructor to be run at this point. Any questions? So what I want to do is just quickly show you guys the fact that all of this is kind of real, and we will definitely spend more time on this on Wednesday. So let me drop this phone. Perfect. So if you haven't tried this already, this will be an interesting exercise in itself to see how this all begins to come together. But I can actually declare, now that I'm doing C++, I can actually declare functions within structs. Notice the compiler error, actually there is no compiler error that's showing up. What I'm going to do is just do something simple here. Just adding a print statement. And we're just going to declare set A. And actually create a destructor as well. We should, just for brevity, I'm just going to give it some members int length and elements. We'll just do this simple thing here. Length is equal to 0, elements is equal to no. All right, make sense? Elements. So actually, to be accurate, I should do this with a this pointer. And here we will just do what we were talking about, which is if this to the length is equal to 0, or I should say is greater than 0, I'm just going to do, at the moment I'm just going to do free this to the elements. We'll do the more C++, this is not the right C++ way of doing it, so I don't want to spend too much time on this at the moment. We'll do it the C++ way next time. C++ way is slightly different, actually slightly better than C. In fact, it'll take away some of the pain points that you've seen with C so far. So if I do a save all, that's actually this thing. So nothing has happened so far. If we go step into, notice what happened. I actually did a step into. This is just a variable declaration. But when I did step into, it actually jumped over to the set function, which is the constructor. And from here, we can actually, you'll see that the constructor will actually get called. And this is not what I wanted to do, but yeah. All right, so the constructor gets called, and then the length and everything happens. And so this is where the constructor is called. The variable A is being declared. Now let's see what shows up. Constructor called actually has shown up on our terminal. Now the main function is about to end, so A is going to go away. It's a local variable, remember, so it's about to go away. So we will actually see the next thing that will happen is that we will be able to jump into the destructor. And the code now jumps straight into the destructor. We will actually get the destructor called, and then the program will actually end. Not what I intended to do again, but. So I guess I'll just leave you guys with one more thing quickly here, which is the freakish idea of actually getting more than one of these functions with the exact same name. So we'll just do set int k printf constructor 2 called. So what we'll do is we'll do set b 5. we are expecting that the second constructor will be called at this point, and let's just do one more thing here. So it's basically going to declare two sets, the two values, and we will actually see the second constructor will actually be called. So I'm just going to remove the debugger from here, put it right here, and just have at it. So worth noting the order in which constructors and destructors get called. So constructor for A is going to get called first because A is the first local variable, right? Then we're going to see the constructor for B. Then we're going to see the destructor for A and then the destructor for B, because A is going to live through the definition of B. So that's why we're actually seeing this right now. If we go step into notice how it actually jumped to the second constructor. And we will just let's see. So notice what happened here. Constructor called, constructor 2 called, and then destructor called twice. Once for A and once for B. So we'll pick this up, and next time we'll jump into the copy constructor, spend a little more time, and learn some more C++. By the way, one announcement. I will not be able to make it to my office hours today. If you have something, I can talk to you right now. Otherwise, I'll have office hours on Wednesday.
So does the destructor get called once we're out of the main function? Does it call itself? Or do we have to call a destructor? Do we have to put tilde set? Or
No, it gets the compiler takes care of it for you. As long as you declare a function with the tilde and the same name as the struct, as long as it's a destructor, the compiler just takes care of it. Just give me one moment here. I need to get rid of.